Hi there, I am Ümit Alkuş. In this video, we will solve one problem from chapter 30. The figure below shows a circuit containing an inductor. At t equals 0, the switch S is set at position 1. A. Calculate the magnitude and direction of the current at t equals 65 microseconds. At position 1, the situation is as follows. Because this is an RL circuit, the inductive time constant tau is calculated by the formula L over R. The inductance is 1 times 10 to negative 3 Henry and the resistance is 25 ohms. If you calculate, you get 4 times 10 to negative 5 seconds. Or simply 40 microseconds. The current passing through the inductor is calculated by the formula I of t equals V over R times 1 minus e to negative t over tau. To obtain a simple formula, we put the numerical values into this formula. If you calculate, you obtain 10 times 1 minus e to negative t over 40, where t is now in microseconds. The magnitude of the current at t equals 65 microseconds is 10 times 1 minus e to negative 65 over 40, which is found to be 8.0309 amperes. Or in 3 digits, it is approximately 8.03 amperes. And due to the orientation of the battery, the current is down through the inductor. B. What is the magnetic energy stored in the inductor at t equals 65 microseconds? The formula for the magnetic energy is 1 over 2 times L times I squared. At t equals 65 microseconds, the numerical values are. Therefore, the magnetic energy is approximately 3.22 times 10 to negative 2 joules, or simply 32.2 millijoules. At t equals 65 microseconds, the switch is suddenly set from position 1 to position 2. C. Calculate the magnitude and direction of the current 10 microseconds after the switch is set position 2. The initial current I0 is now the current at 65 microseconds, which is 8.0309 amperes. Then the new inductive time constant is tau equals L over R, where L is 1 times 10 to negative 3 henries, and the resistance is now 50 ohms. The calculation gives you 2 times 10 to negative 5 seconds, or simply 20 microseconds. The current at any time is found by the formula I0 times e to negative t over tau. Insert the numerical values into this formula, where t is in microseconds. At t equals 10 microseconds, we have the current as approximately 4.87 amperes. And the direction of the current passing through the inductor is downward, because inductors don't like the change in the direction of the current. D. When, after the switch is set position 2, does the current reduce to 2 amperes? Now, the final current is 2 amperes, and the initial current is 8.0309 amperes. The relation between them is IF equals I0 times e to negative t over tau. To find the time, we do the following. And taking the natural logarithm of both sides, you obtain ln of IF over I0 equals negative t over tau. And the time is found by the formula negative tau times ln of IF over I0. Now put the corresponding numerical figures into this formula to obtain the time when the current reduces to 2 amperes as 27.8 microseconds. Okay, that's all about this problem. Thank you for your attention. See you on the next video.